Alright, hello and welcome to GIS 1470, Introduction to Geographic Information Systems, Lecture 2. For this lecture, we're going to be looking into the basics, foundations, and history of geographic information systems. Oh, ignore that. Alright, so at this point I want you to think about what comes to mind when you hear GIS. To yourself, obviously, because it's a recording, just think about what those things are. What does it mean to you? Are you thinking about GPS? Are you thinking about Google Maps? Things like that. If so, you're on the right track. But oftentimes, what GIS stands for is misinterpreted. Uh, that could be because the S in GIS can change depending on what we are discussing. Like a geographic information system, it could be a database with a front-end cartographic visualizer that may or may not offer spatial analysis tools. Geographic information science is in reference to the study of the theory of spatial science and its underpinning concepts. It's closely related to geodesy, cartography, and geosciences. So think about what your definition of a GIS is in your head. And depending on how you're currently using GIS, that definition might be different. So what do you think? Do you think you have the right definition or the wrong definition? Well, chances are you have a correct definition. Geographic information systems are broad, just like the science, so there's no one fair definition for it. So throughout this lecture, start thinking about what GIS is to you, how you would define it based on your use of it. Another question that is often posed is whether or not you do GIS or you use GIS. The correct answer is generally that you're going to be using it. What you're doing is you're applying science to your study, and you're using GIS in order to further that goal. So Ron Abler is a geographer at Penn State and is a longtime fellow of the American Association of the Advancement of Science. He first saw GIS as an organizational tool to bring the spatial information and data of the world into a unified system. He often referred to geographic information systems as being simultaneously the telescope, the microscope, the computer, and the Xerox of regional analysis and synthesis of spatial data. The description of what a geographic information system can be makes GIS a supporting science that can improve and enrich other fields of study. Just look at what GPS receivers have done for the profession of land surveying. They provide high precision, horizontal, and vertical accuracy with a single lightweight instrument compared to the historic transit and steel tape. Or you could take a marine biology approach and look at what GPS-enabled shark tags have done to shark studies, allowing continuous tracking of tagged sharks versus tedious and hopeful sightings. Thanks to GPS-enabled shark tags, we're able to actually see where these sharks are traveling at all times and potentially identify where they're actually reproducing. So now you should start to kind of have an idea or an understanding of the value of the purpose of what GIS can do for you, even if you don't know exactly how you're going to be using it yet. All right, so what is GIS exactly? Of course, there has to be a definition somewhere. So common definition for a geographic information system is a computer-based system to aid in the collection, maintenance, storage, analysis, output, and distribution of spatial data and information. An important difference between the information technologies and the geographic information systems is the addition of the spatial attributes and tools to the existing data, and sometimes exclusively spatial information. Today, spatial data is exploited by almost every single industry that exists. So because so many industries use GIS and they use it for so many different purposes, there is no single definition or one system that's going to fit for everyone. However, it is important to geographic information scientists and professionals to recognize the specific industry definitions and benefits so that we could better serve them, i.e., most of you. If I am building a GIS to help manage a company's pipeline network, I'm not going to structure it off the same GIS that I built to help Amazon deploy targeted ads to you on Facebook. While the foundations and principles of them are the same, the structure or the bones of it will be different. I'd like to use a construction-based analogy. All foundations are going to be the same materials, the same composites. Every now and again, we might add rebar to add extra support, but they're all relatively the same. It's not until we actually look at the structure that we put onto the foundation that we start to see differences. Are we using a wood frame home? Are we doing steel framed homes? Or maybe we're using recycled processed plastics in order to help reduce waste. The purpose of these geographic information systems are completely different. So, despite being built from a similar foundation, you must adjust your structural approach depending on the needs. You're going to see this a lot in your own fields after you leave here, after you leave college. So, for those of you that might be student research assistants currently or involved in specific research projects with faculty mentors, think about what you're researching. Keeping a simple, broad view of what that is, think, would a GIS benefit your research? Would identifying spatial distributions or locations of aspects of your research help it? I don't know. It's a question for you. So like we just discussed, many academics in academic disciplines view GIS as a tool. It's an addition to softwares like R or Access or MATLAB or AutoCAD. And there's a heavy use of statistical analysis and spatial distribution models that can identify areas of likelihood or even species cohabitation in the GIS toolbox, as they like to refer to it as. Peter Bureau said GIS was a powerful set of tools for storing and retrieving at will, transforming and displaying spatial data from the real world for a particular set of purposes. Excuse me. My most common particular set of purpose for a GIS is developing land administration systems that contain land records, i.e. maps, deeds, reports, bills of sales, old plats, and then being able to perform some form of spatial search or a visualized spatial search of the said land records. The beauty of this is that now I'm able to find related documents based on their location, opposed to finding one document and then hoping I could find the other pieces of the puzzle. GIS, in my case, helps bring it all together. Roger Clark, who's the current commander of the U.S. Air Force Space Command and the 21st Space Wing, but not the Space Force, sees GIS as an automated, sees GIS as an automated system for the capture, storage, and retrieval, analysis, and display of spatial data. The Air Force is responsible for collecting real-time satellite imagery in support of U.S. military operations around the globe. The value of having a geographic information system in place that will allow for the instantaneous analysis and visualization of satellite imagery is absolutely crucial. A question about the accuracy or the resolution of this data was brought up in class. It's important to note that depending on the orbit or the particular satellite that they'll be using at that moment, we'll get different resolutions, different levels of accuracy out of it. So we're not always looking at sub-centimeter accuracy. Sometimes we're looking at something in the range of 5 kilometers. But that's because we're working in a very rapid environment, and the way that satellite imagery works is that we literally have to wait for the satellite to complete its orbit around the world before we're able to collect a different level of imagery in that location. So the science behind these systems is done using established theory and founding principles of spatial science within a developed software that supports spatial operations, i.e. geographic information systems. The greatest issue with GIS is the same issue that impedes all information technologies: quality of data and education of the end users. There are many people that use geographic information systems or spatial data without proper understanding of geographic information science. A good example is the common misuse of spatial data at incorrect scales or resolutions. Many times, historic data that represents a large area will be used to define an area or a enumeration unit that is at a smaller scale. Using historic Landsat data to identify exact wetland boundaries is a good example. If the resolution of the imagery is at 5 kilometers, how are we supposed to use that data to define a 3-kilometer stretch of wetlands? The answer is you can't, but there are a lot of people out there still today that are doing it because of the prevalence of the information. Another common issue is not displaying spatial information in the correct format. This is often seen with map figures produced by news media outlets. We won't get into that in this course, or probably any course except for poli-sci, but if you do decide to take visualization with GIS, you'll learn about the different ways that you can visualize data. So GIS has become an extremely profitable industry in itself. The South African company Esri is the most successful GIS software developer to date. TMUCC is fortunately an Esri academic center, so all of you will get the ability or the opportunity to use the industry's leading software in your labs for this course. We're going to specifically be using Arc Pro, which is the latest, and it's being picked up already in oil and gas industries and municipality industries. So Jack Dangermond, who is the executive and co-founder of Esri, he and his wife turned a $1,100 investment in 1969 into $1.1 billion in revenue in 2017. All right, today, Environmental Systems Research Institute, Esri, has 350,000 customers, including federal agencies, health departments, and schools. So geographic information systems have become commonplace in everyday use. From apps like Waze, which utilize user-generated spatial content, to GPS-enabled cameras on smartphones that allow you to use geotag pictures. It's there. It's on everything. It's in Facebook. It's on Instagram. It's in Snapchat. But why is it there? What's the added benefit to it? Well, things like Waze, they focus on user input. Waze doesn't actually look at the traffic and identify potholes and locations of police up the road on its own. It requires someone with the app to see that incident first, see that event, and then they're able to put it into the app, and then it's now shared with everyone else that's using the app. Waze has actually been fortunate enough to get picked up by Google, not bought out, but they now have a collaboration project with Google. Other apps like Sirius Radio will offer you specific deals or specific stations depending on your location. The cameras on your smartphones, iPhones, and higher-end Samsungs will allow you to add coordinates or identify your location when you're taking pictures. A benefit to this is, say you're out doing a site survey for a wetland study or a potential wetland study, but then you identify potential hazardous waste materials. Well, when you go back in your report, you're going to probably want to include a picture of that waste material in there and a description of where it was seen at. Well, if you allow the camera to tag your location to that picture, you'll not just be able to give a description of where it was taken, you'll be able to actually use the coordinates of which it was captured. So someone could take that image, so to say, throw it into Google Earth, and it'll generate exactly where you took that picture to show them exactly where it's located. It's just higher accuracy and more enriched data. So now we're going to get into the history of GIS. GIS has a background in geography, cartography, computer science, and math, predominantly statistics. Those are some of the backgrounds that are looking at GIS now as a graduate degree, people who didn't have the opportunity to learn about GIS when they were in school, but are using it now in their day-to-day lives. GIS has become a fusion of information systems and imaging and positioning technologies, such as GPS. We're taking traditional databases and we're giving them spatial attributes, we're giving them spatial information, and being able to then visualize information that's in there that's not spatial by default, but it is spatial by association. So a good example of that would be, say we take a neighborhood and we're trying to identify parts of a neighborhood or a subdivision that have higher land values. assuming it's an unrestricted area, so there could be big changes in land values, but that's irrelevant. um, we can then take individual parcel information or locations, which are spatial in nature, and then associate the value of each of those parcels, which is not spatial by default, but is by association to the parcel's location. Then we can do an aggregation to identify which areas of the neighborhood have higher value properties or homes and which ones have lower value property or homes. It's important to you to consider things like that, say when you're buying a home, because the value of your neighbor's house does directly have an effect on your home. So geographic information science is an interdisciplinary field, and it's built out of the use and the theory of GIS. More heavy, honestly, on the use than the theory. If there weren't people who were using GIS in their fields, in their industries, to help further their own goals, it wouldn't have pushed GIS to become the giant industry that it has become today. And it's out of that widespread use that we've established theory, we've set standards, developed guidelines for use in GIS. All right, so more history continued. GIS origins also lie in thematic cartography and regional planning. We'll see some examples of that here in a minute on how GIS in reality has been used since the late 1600s and 1700s. So many planners in the 1950s actually used methods of map overlay using manual techniques. I posed the question of the class, how many of you, before you came to college, remember using overhead projectors in class, where you would have the different transparent sheets set on top of each other to do different problems. Well, the same concept for a long time was used with maps. We would take the different layers, whether we're looking at man-made objects, terrain, environmental factors such as topography, things like this, as different sheets, and they would be overlaid on top of each other manually. So the manual map overlay method is described comprehensively by Jack Linth-Wright in a 1950 planning textbook, but its roots go even further back to Ian McHarg's early work as well. So here's some examples of GIS products and how they've been used in the past. On the left, we're looking at where you can see it's all kind of the different squares. We're looking at regional planning of a village in the United Kingdom. And what they're able to do here, what they were able to do here in the 1600s was essentially zone and identify different purposes of land use or what they were going to put where. Those of you from Houston have no clue what zoning is because, it's gas station, neighborhood, medical complex, $1 million neighborhood, 5th Ward, so on and so forth. I say that because I'm from Houston and it drives me crazy. On the top right, we're looking at a 2.5D technically, because it's not actually three-dimensional, a 2.5D map looking at terrain, relief, and vegetation cover of an area. Whenever we refer to something as 2.5D, we mean it's still physically drawn two-dimensionally, but it's showing three-dimensional change. And in the bottom right, we're able to see different map figures looking at soil types and drainage maps. Figures is something that a lot of you are likely going to come out of here and use in your future studies. If any of you do graduate school, you're going to be using figures quite a bit to help enrich your research or to visualize the research that you're doing. Because nobody wants to just sit here and look at a 40-page spreadsheet of line-by-line information and the different attributes associated to each row. It's a lot easier if we visualize it, put it into a map or a figure so that it's very easy for someone else to interpret or even for you to interpret. So in the 1960s, we saw new forms of geographic data and mapping software come around. A lot of this had to do with the prevalence of computers and that they were entering in the workforce a lot more. So not necessarily personal computers that you have home, but workstations that had specific tasks and functions in our workplace. Computer cryptography developed the first GIS concepts during the late 50s and the early 60s. This goes into our manual overlay concepts. What they eventually were able to do from that was they would have these large tracing tables with lights that would come up from underneath, and you would set the objects on top of it, and then it would be attached to a computer with a separate screen. And there'd be a special pin in which you're able to literally trace paper maps that were created, and it would then take that information and store it onto the computer as its own file. That's the earliest stages of digitization. One of my past mentors in the GIS, Seneca Holland, actually started out her career in GIS digitizing maps. And eventually we got to the point where we linked software modules rather than standalone programs which preceded GISs themselves. Instead of trying to build early archaic-based systems, we just built specific tools that could help benefit existing software packages that exist. This still happens a lot today, and a lot of you that aren't GIS majors are going to end up doing things like this. Say you're doing statistical analysis using R, which is a very common statistics software package opposed to MATLAB, which MATLAB also has this, but it has add-on modules that will allow you to essentially create visualizations from the processes and the algorithms that you're running in R or MATLAB. Other early influencers were large data sets like the World Data Bank and Tiger Files. The World Data Bank likes to collect a broad or very wide general amount of demographic data around the world that specifically focuses on things like poverty. Tiger Files are collected by the U.S. Census Bureau, and they focus on looking at boundaries and objects within the United States of America. GIS was again significantly altered by the personal computer and the personal workstation. What this did was it gave people at home the ability to now use GISs in a way that enriched their own individual lives. One of the earliest GISs that I remember growing up was, logging into AOL and then accessing MapQuest. MapQuest is one of the original mapping services to map travel that predates things like Bing Maps and Apple Maps and Google Maps.
Ryan's a dinosaur.
And that's my wife right there. In the 1980s, new GIS software better exploited this advanced hardware. Now that we had better, faster, stronger, and more affordable computers, we had a reason to make standalone GIS systems that can kind of do everything that you want in a GIS without it having to be antiquated or very limited as it had been in the past. User interface developments led to GIS's vastly improved ease of use during the 1990s, like what you're going to see in your labs using ArcPro. Some open source GIS that exists and is commonly used today that we'll talk about in a little bit doesn't have the easy to use interface of things like Esri, but they're free, which makes it a lot more attractive to especially small businesses and small environmental firms. All right, so parts of a GIS. GIS in reality is a bit of an umbrella. At the top of this umbrella, we're going to have our data. All right, that's what's coming down, raining on us, and the umbrella is going to protect us from the data that is crashing all around us. All right, that umbrella is going to do, how it's going to do that is it's going to give us software that's able to manipulate and interpret this data. It's going to focus on developing specific hardware systems that can handle large data sets and properly visualize the software that we're using. It's also going to include methods that we're using in order to establish how we're going to use GIS and what are our principles, what are our foundations. And lastly, it's also going to be served by a network that reaches into tons and tons of different fields, as well as a network of computers in which is able to then disseminate information and share information. And who's this umbrella for? It's for people. It's for end users, people like me who specifically dedicate their lives to GIS and building proper GIS systems. and to people like you who are going to be using GIS for your individual studies, not as a main focus, but as an enrichment thing. So you're not going to focus on building a GIS or developing new state-of-the-art algorithms. Your focus is going to be on how can it help me? How can I use it? And of course, there's the just general public who uses it, when they're tagging their photos in Instagram or something. All right. So what all actually falls underneath our umbrella of GIS? Well, we have things like data services, which focuses on collecting data and then selling the data off to people like me or you. All right. And then there's data analysis, which is going to focus specifically on actually assessing data, manipulating data, and trying to derive products from it. And there's remote sensing, which is going to focus on things like satellite imagery or LiDAR, data collected with LiDAR technologies. There's mapping, whether it's focused on looking at actual land or just general information that has spatial qualities. There's cartography, which is the actual art, science, and technology of map making, which is going to want to ensure that GIS is actually appropriately accommodating the rules established in cartography. And there's programming and scripting, which is newer and it's becoming more and more relevant every day, really. So thinking about whether or not you might fall under this umbrella, these aren't the only bullets, the only things that actually fall under here. These are just some general examples that we often look at. All right. And we also have 6 major parts of a GIS. We have hardware, software, data, methods, people, and our network. Let's get into each of those. So our first part being hardware, it focuses on having powerful computers in which are able to handle the analyses and the software demands that GIS is producing. Right? We need to have printing and plotting and other visualization capabilities. Printing and plotting is still important today because a lot of people still physically like to hold maps in their hands, but other visualization outputs have become more of a trend. Everyone has a phone in their pocket which they're able to open up Google Maps on. People have tablets in which they're able to share information on. The recent affordability of large televisions has introduced those into a lot of workplaces. So you're not going to go into a workplace meeting and see a paper flip chart so much anymore. You're just going to have a large screen in which you're visualizing it. It's important to recognize the differences between digital visualizations of information versus tangible visualizations of data because color methods that go into that are different, and you have to make sure you're using the appropriate ones. Otherwise, it won't look right. But we'll get in, not in this class. That we'll get in more if you take visualization with GIS. We'll get into that. All right. We have to focus specifically on our input devices. Are we able to take the instruments in which we're collecting data and transfer that data onto our computers? Is there hardware that supports that? Does the software support it directly to where we can plug it in directly? That way we're not having to convert it to multiple different files just so that we can open it in Arc Pro. And then we're going to typically need large amounts of disk space, whether this is physical space you're controlling, physical servers in which your firm or company is managing, or if you're using cloud storage, which is becoming a lot more common. In class, I mentioned how cloud storage isn't actually information being stored in the air. It still goes into a physical server. It's just not managed by you. It's managed by like Google or Amazon Web Services or something of that sort. In case you didn't know. All right, second part of GIS is software. The purpose of software is to provide tools that can manipulate, store, query, and analyze our spatial information. We like to be able to manipulate it, meaning that we can move it around, we can zoom in and out, we can skew it, we can translate it, transform it, all those things. Then we want to be able to store it. Software that specifically lets us save it in formats that's useful, whether it's a digital format or an actual physical format, so it has a plotting service associated to it. We want to be able to query our spatial information, and this, I think, is one of the most important ones. We want to be able to actually search through it, be able to search each field, build complex search queries that allow us to truly identify exactly where a specific location that we're desiring might be. And then we also have to be able to analyze spatial information. We need to be able to run analysis, identify hotspots, aggregate our data, and things like that. So there are a lot of free and commercial software packages out there, but the big three really are Esri, which is a paid-for commercial service, Grash GIS and QGIS, which are both free services. Grash GIS was developed by the United States Army back in the day, and they have since made it an open source software package that anyone can download and use. QGIS is another one that focuses a little bit more on statistical spatial analysis and things like that, opposed to GRASS, which will look at things like hydrologic models and whatnot. We'll be using Esri in here, of course. As I said, we're lucky enough to be Esri Education Center. All right, our third part of a GIS is data. So GIS needs to be able to ingest any type of data, both spatial and non-spatial. Like I was saying before, a lot of information or data might not be spatial by default, but I guarantee there's a way that it can be spatially associated to something else. So whether it's, property values or, a picture, we could look at where we took it, or, it's known speed traps in an area based on the fact that we know that there's huge, 30 mile per hour drops in speed when you hit this point of, I-35. All right. Like I said before, there's a lot of data, and this is why we need the umbrella, because we're currently in a bit of a data overload state. And the same thing could be said with almost all type of information because of the internet. There's so much information out there. It's everywhere for everything that you're looking for. But most of this information has never been vetted. So even though a lot of it might have been collected and hosted with good intentions, they're actually doing a huge disservice because the data itself is wrong for some specific reason, whether it was based in the collection method or some type of corruption issues. And of course, as we've seen with a lot of information in the past few years, a lot of wrong data, incorrect data is intentionally put out there just to add confusion and things like that. And that happens in GIS as well. Then we also have visualization of data. As humans, it really helps us to see things on a map, to identify, what's happening where, to see trends. It's just intrinsic in our nature. We're able to look at a map and identify what's happening where, whether we're using colors or symbology to do that. It's a lot easier than, like I said earlier, looking through hundreds or tens of thousands of lines of data, just row by row, and then trying to see trends in that. It just doesn't happen. Statistics is great, but statistics isn't great. I lied. That's not true. I don't honestly feel that way. Some people might, you might, but I don't. Statistics are very powerful, but they can't do everything. All right. Half of all GIS projects, including the ones that you'll be doing here, is going to mostly revolve around working with the data. It's going to be a large portion of every assignment that you do here. The purpose of that is that I'm trying to familiarize you with spatial information, with spatial data. The labs and stuff that you'll be doing in this class are going to focus on just learning how to do different functions within ArcPro. It won't do us any good to immediately expect you to do specific tasks if you don't actually know what those tasks mean or what they do. So right now we're just looking at, this course is going to focus on capabilities and potential use. 4, we need to look at methods. The image that you're seeing on this screen is a snippet from ArcPro looking at the query builder. And it's focusing on essentially building a task within ArcPro to run on your data. The value of this is that you're able to save these models and use them over and over again with different input data. So methods highly focuses on things like our formulas, our statistics, analysis, and algorithms. Those things of sorts. This is where most people tend to think, oh, GIS is too hard, I don't want to do this. But if you can get through this part and you can understand the methods of GIS, you'll really be able to enrich what you're doing and make yourself a more attractive employee to whoever your future employer is. All right, 5, we're looking at the people. People are one of the most important parts of GIS, but we have different tiers of people. This here is Jack Dangermond. He is the the owner of Esri. All right, and he is a GIS professional. Um, I, at this point in my career, I think would consider myself a GIS professional. I'm actually building systems, building databases, and enriching information to put it out there accurately, not just like, oh, hey, here's something, maybe it's good, maybe it's not. Then we have novice users. This here is looking at the past graduating class after their capstone presentations in the GIS program. A lot of these people now, they're on their way to becoming professionals with the jobs that they're at now. But that doesn't mean that everyone who learns about GIS and then graduates, or who takes this course and graduates, is going to become a professional user. Many of you, I would still consider novice users because you're only focusing on running specific tasks or operations dependent on your field of study. You're not focusing on the overarching picture, which I'm sure a lot of you are happy that you don't have to do that. All right, and then of course there's public users. Every single one of us in this room has been a public user of GIS at one point or another. We've used Google Maps. We've used Amazon shipping services or something similar to that. We've all done it, and there are a lot of other people who don't even know what the heck GIS is that are using it every day unknowingly. So this tends to be the customer of GIS, and we need to make sure that we're building accurate and reliable GIS systems, or in your case, or most of your cases, performing accurate GIS analysis or analysis to enrich the work you're doing. Because if you're not doing it right, all you're doing is causing more of an issue. All right, and lastly, we have our network. All right, networks in GIS refer to essentially the dissemination of data, the transfer of data sets, being able to take the data I collected and not just use it, but then share it with you. Here in the image, we're looking at not weather radar, but ecological regions out in Harris County or around the Houston area. All right, there's also collaboration. That means that I don't need to just be able to share data with you. I need to be able to work on data with you. There are a lot of platforms today, of course Esri has one, ArcGIS Online, that allows multiple people to work with a single data set at the same time so that we can build things together. This is really popular in things like disaster management and emergency response. All right, our networks also have to focus on the display of information. We can't rely on paper copies of everything anymore. All right, if there is another Harvey that causes mass flooding in Houston, we can't wait for mail to be shipped to Houston because first of all, you need a dang boat to get it there in order for them to use it. All right, if we had ways of uploading it to the web, because the emergency response groups will have sat feeds, sat feed internet in order to access these type of things. And we need web-based applications that can be used both online and offline. That way we can collect data when we're outside of service ranges, but then automatically have it synced to the system once we're back in a connection. And then, of course, there's the network of people together and just the general field of scientists communicating and working together to identify, what might be needed where, what should be developed, what do we not need to focus on so much, things like that. All right, so now you're posed with the question, how can GIS be used? This is a question for you as an individual. All right, and it's important to use this course, or important to think about this question, and then to use this course as an opportunity to see how you can use GIS in your future careers or even your research here on campus. I'll give you a hint about exam 1 as well. I'm going to ask you to write a short essay as part of it, and I'm going to want to know how you can use GIS in your studies or career. I'll be looking for a legitimate answer that's from your own unique perspective. I'm not looking for textbook responses, and I don't want to have very generalized answers. I want to know how you think you can use it, how it can help you. The only way to get this wrong is to not actually give me an opinion from your perspective. So it's a good idea to just think about it as we're going now, especially as you're taking your other classes. See how GIS can be used there. Some basic examples for GIS in use are things like cadastral information systems. So that focuses on land administration, looking at what land information exists where and what is all the additional information that goes into it. All right, 3D analysis for looking at things like topographical effects, water flow activities that could exist, drainage opportunities that could be exploited naturally opposed to have to building irrigation systems in agriculture. There's deliveries, FedEx, UPS, Amazon all use it for their trucks and how they route, where their trucks are going. Amazon is even looking to use GIS now for how they can deliver your packages using drones. That's still a thing, and they're still trying to make it happen. And one day it will. I don't know how I feel about it, but hey, I can't stop it. All right. There's just the mapping industry. They're going to use it widespread. The New York Times already has an entire GIS department, and albeit they do a lot of really bad work because they're using journalists to create these maps opposed to actual GIS professionals. But hey, it's there. People are using it. Maybe one day they'll do it correctly. The military obviously is going to value GIS quite a bit. They're going to use GIS for things for all their different types of operations. I really shouldn't go into specifics on that. Redistricting, so the Congress can use it for identifying how voting districts should be laid out. I think GIS would do a lot better job than lobbying and gerrymandering, but that's another thing as well. The farming industry uses it rapidly to monitor crop health, identify specific stocks that are having issues or specific areas of soil that might need enrichment. Previously, when they see a bad yield, they just have to redo the whole farm, or if they see poor crop, they have to throw the whole thing out. If they're able to specifically identify areas of issue, they can go in and correct those, saving hundreds of thousands of dollars and hundreds of man hours as well. The health industry uses GIS quite a bit. They use it to track health outbreaks. Right now in Harris County, we're seeing all the measles and the mumps outbreaks because of the jackasses who don't want to vaccinate their children. So that's something that they're using. They're able to essentially identify areas that are at higher risks based on people who go in for treatment. All right, the wildlife mapping, it can be used, like I said before, for tracking shark species or even bird species. Data mining. Twitter is a fan of GIS. They use it to. They use one of the best examples that Twitter using GIS was during, I think it was the season 6 premiere of The Walking Dead. Twitter went through, or the Walking AMC, who shows The Walking Dead, data mined through Twitter to identify who was talking about The Walking Dead and where they were talking about it, where they were when they were talking about it on Twitter during the premiere. And what they did then was they were able to identify areas that were highly populated but weren't really watching The Walking Dead or talking about The Walking Dead on Twitter as much. And then they were able to then focus their resources on putting targeted ads to advertise The Walking Dead in those areas. I know it's just a TV show, but hey, it's a TV show that probably brings in millions and millions of dollars, so it's a big deal. Disaster management. GIS was used a lot in the response to Hurricane Harvey. TMECC was actually able to deploy small UAS operations all through Mustang Island and Port Aransas in order to identify areas of destruction, potential environmental hazards that could have been a result of the hurricane and things like that. It was also used widespread in Houston for rescue operations. They're able to try to see where maybe people could be trapped in buildings that were destroyed, people that were on rooftops that, if they were laying down, they might not be able to see from boats that were traveling up and down the flooded streets. Natural resource management uses it, infrastructure uses it, and of course, just decision support. GIS helps us understand the vast amount of information that's out there. So that's where decision support the support comes in. We have information and data that makes sense, that we can easily identify trends for. So we have more information so we can make more informed decisions. Someone just teach that to Congress. All right, here are a couple visualizations of different GIS uses. On the top, we're looking at creating 3D models of mountain peaks. On the top right, we're seeing a large drone being used for military operations. Just under that, we see a bird with a GPS-enabled tag on it, so we're able to see where this species of bird might be hunting, might be mating, and might be breeding. On the bottom left, we see kind of the general scope of all the different things we can do with GIS. And on the bottom right, we see a bit of an abstract view of remotely sensed agricultural data, of different crop data that can identify crop health or soil health. All right, lastly, we have this short video. Oh, that closed. I'll make this work, I promise. You're gonna watch it, damn it.
Where digital transformation is taking place and the world changes in the blink of an eye, Esri users are unlocking the full potential of data to solve real problems in real time. They use location and geography to integrate, analyze, and understand all types of data. They embrace the science of GIS, science that Esri pioneered, and its users continue to advance. Organizations everywhere see data in new ways through a common visual language. Informed, inspired, and empowered by the science of where, pushing the boundaries of geography to create deeper insight and understanding. The science of where is the science of exploration and navigation. The science of the grand and the granular. This is the science of development and the science of sustainability, the science of power and the science of peace, the science of will, the science of wonder, the science of where.
All right, so that was just kind of a broad overview from Esri looking at how GIS is used and why it's important. You will notice in this class that I am going to use a lot of videos and graphics and things from Esri. It's not because I'm trying to sell you on using Esri for the rest of your life. You know, they just made $1.1 billion last year, so they have plenty of money to make great PR videos and graphics and things like that. So I'm going to use that. Otherwise, you're going to have to look at the stuff I make in clip art. And while it might be funny to look at, it's not going to be helpful for you to learn anything. All right, so that's it for lecture 2. I hope this first recording comes out great for y'all and you find it useful. Just a reminder, I will continue to make these recordings for every lecture in this course. Also, just in case you're watching this tonight because you missed lecture today, I will be, you will see emails coming through of Esri accounts being created for you before next Tuesday. That way, when we go to lab next week, Tuesday and Thursday, you'll be able to log in to ArcGIS Pro because it's not just a simple desktop application anymore. You need a specific account to log in. If you already have an Esri account, that's great, but I'm still going to create this one that's specific to this course because I'm going to need to make sure that I remove it after we leave this course, and I don't want to have to delete your own, your regular Esri account. All right, thank y'all, and I will see y'all at lecture 3, or not see y'all, but talk to y'all at lecture 3.